Welcome to Grandeur Decoded, where we examine the structures and strategies that reveal what human capability can achieve when the stakes are high enough. Few places on Earth face the combination of population density, infrastructure complexity, and environmental risk that Tokyo does. Beneath this megacity lies a hidden engineering system many residents will never see, yet it stands ready to protect tens of millions of people during the most extreme storms. The metropolitan area outer underground discharge channel, often called the Japanese Flood Fortress, is one of the largest and most complex flood control projects ever created. Today, we decode how it works and why Japan built it long before climate change became a global concern. Remember to subscribe so you never miss a deep dive into the forces shaping our world. Fact 1. Tokyo's geography guaranteed recurring floods long before modern climate change. Tokyo is built on a broad alluvial plain where multiple rivers converge. The Naka, Otoshi, Kuramatsu, and Arakawa rivers all carry runoff from surrounding basins into flat terrain with limited natural drainage. For centuries, seasonal rains pushed these rivers beyond their banks. As the city expanded during the 20th century, paved surfaces replaced wetlands and soil that once absorbed water. Concrete channels sped river flow in some places while causing dangerous backups in others. By the 1970s, even moderate storms were producing increasingly disruptive floods. Engineers warned the government that Tokyo's geography created a structural vulnerability that would only worsen with continued development. Fact 2. Modeling in the 1980s revealed the city was approaching a tipping point. Japan commissioned a hydrological study in 1987 to evaluate future risk. Analysts combined meteorological data, rainfall intensity trends, soil saturation models, and simulations of rising sea influence at river outlets. The results shocked policymakers. Once rare extreme rainfall events were becoming more frequent. Rivers would not have the capacity to carry peak flows. Existing levees would be overtopped in multiple districts at the same time. Transportation routes, power substations, and residential zones could all be submerged within hours of a major storm. The report concluded that without an unprecedented intervention, Tokyo faced predictable and severe economic and safety impacts. Fact 3. Subsurface water storage emerged as the only viable solution. Engineers understood that expanding rivers or raising levees would require massive relocation of communities. Adding more concrete channels could shift flooding into new areas. Surface-level strategies alone would not work. The design committee proposed a different approach. Capture excess river water underground, where space is more controllable. Move it horizontally through deep tunnels. Temporarily store it inside engineered chambers. Release it safely when river levels fall. This strategy allowed Tokyo to create volume that did not require surface land acquisition. It also made it possible to regulate water flow, even during long-lasting storms that would overwhelm pumps operating alone. Fact 4. Construction of the intake shafts required some of the deepest urban excavations in Japan. Beginning in 1993, engineers created 5 intake shafts positioned near critical river junctions. Each shaft descends about 70 meters into the earth and measures roughly 30 meters across. These shafts act like funnels, receiving diverted river water when levels rise past thresholds. Building them required ground reinforcement to prevent soil collapse, continuous pumping to control groundwater, and the installation of structural rings strong enough to withstand both water pressure and seismic motion. Each shaft is large enough to hold a multi-story building. Their placement had to be exact because each one feeds a specific branch of the underground network. Fact 5. A 6-kilometer tunnel system links the shafts to a central chamber. At the base of each shaft, floodwater flows into tunnels carved deep within the subsurface layers. The main tunnel extends more than 6 kilometers, passing through soil, clay, and sediment that had to be stabilized to prevent deformation during earthquakes. The tunnel lining consists of reinforced concrete formulated to resist both constant moisture and dynamic pressure changes. Engineers also included inspection corridors and embedded sensors that record stresses along the length of the tunnel. This allows for early detection of structural changes before they become problems. The entire system functions like a controlled river that exists below the real ones. Fact 6. The pressure regulation chamber is one of the largest enclosed spaces ever built for flood control. The main chamber, often called the underground temple, stretches nearly 200 meters in length and rises almost 18 meters in height. 65 concrete columns line the chamber, each weighing about 500 tons. These columns serve a mechanical purpose. They break incoming water surges into slower, more stable flows. Without them, the force of water entering at speed could generate turbulence strong enough to damage the chamber floor or create pressure pulses that travel back into the tunnels. Engineers shape the columns to reduce cross currents and promote laminar flow, allowing the system to stabilize during peak intake. Fact 7. Real-time monitoring and manual decision-making are essential to system safety. While the fortress incorporates automation, humans remain central to its operation. Teams monitor data from rainfall gauges, river level sensors, soil moisture readings, and predictive weather models. Operators determine exactly when to divert water into the shafts. If the system is activated too early, the tunnels could fill before the peak of the storm. If activated too late, surface flooding may begin before diversion occurs. This system requires perfect timing. Operators train using simulations that recreate past storm events, including Typhoon Mindul, which tested the system's capacity in 2004 and proved its effectiveness. Fact 8. The pumping station contains turbines powerful enough to move entire river segments. At the far end of the regulation chamber sits a row of enormous turbines. Each turbine can move about 200 cubic meters of water every second. Combined, they can push enough water into the Edo River to fill large water tanks in seconds. Engineers designed vibration-absorbing foundations beneath the pumps because the forces generated during operation are intense. These turbines allow the fortress to empty itself once the storm has passed, clearing the tunnels and chambers for the next event. Their reliability is critical because Tokyo often faces multiple storms in a single season. Fact 9. The system has repeatedly prevented catastrophic flooding. During Typhoon Mindul in 2004, rainfall overwhelmed upstream basins and river levels climbed rapidly. The fortress diverted the surges that would have flooded major districts. In 2007, another intense rainfall event occurred, and again, the system intercepted water that would have damaged infrastructure. Hydrologists estimate that the fortress has prevented billions of dollars in losses since becoming fully operational. It has become a global case study in proactive climate adaptation and urban resilience. Fact 10. Japan treats the fortress as a living system that must evolve with climate realities. Japan conducts regular inspections with robotic crawlers that capture images of joints and reinforcements deep within the tunnels. Engineers monitor long-term wear, test pump performance, and evaluate chamber conditions. Climate projections indicate storms will become more intense. This has prompted discussions about expanding storage capacity, extending tunnel networks, and introducing more powerful turbines. The fortress is not considered complete. It is considered adaptable, which is the mindset that allowed Tokyo to avoid the severe flooding that other megacities have already experienced. This underground system represents a national decision to invest in prevention long before disaster strikes. It is a reminder that engineering can protect millions when it is planned with foresight and executed with precision. If you enjoyed this documentary exploration, remember to subscribe. Grandeur Decoded will return with more stories revealing how human ingenuity shapes the world we live in.